So here we are going to understand mathematically how buffering capacity works, because if we look at it mathematically, we can truly understand and appreciate how buffering capacity is correlated to buffer concentration. Now, going back, we have learned that in order to prepare a buffer, we must have a component that is able to neutralize acid and a component that is able to neutralize base. And when we talk about preparing buffers, there are 3 different ways we can prepare a buffer. We can have a weak acid and conjugate base in a 1-to-1 ratio. We can have strong acid and weak base in a 1-to-2 ratio. And then we can have weak acid and strong base in a 2-to-1 ratio. Now here we are going to be utilizing this first buffer preparation as an example to understand buffering capacity, but it is important to understand that the mechanism behind all 3 is the same. Now, theoretically, the textbook definition of buffering capacity is defined as the moles of H plus or OH minus needed to decrease or increase the pH of 1 liter buffer by 1 unit. Now, H plus denotes acid and OH minus denotes base. If we're adding in acid, we are going to decrease the pH. If we're adding in OH minus, we're going to increase the pH. So we're understanding how much of acid or base do we need to deviate 1 liter of buffer by 1 pH unit. And this will make sense once we go over the 2 examples. Now, this theory essentially just tells us that the concentration of buffer is going to be directly proportional to the buffering capacity. Essentially, the ability for a buffer to minimize the change in pH is dependent on how much buffer we have. Now, taking a look at example number 1, let's say we have 10 moles of buffer. If we have 10 moles of buffer, let's take a look at our equation for a buffer. So if we have HA, which is our weak acid, it's going to partially dissociate into H plus and its conjugate base. Remember, weak acid plus conjugate base gives us a buffer. Weak acid, conjugate base, it's a partial dissociation and they exist in equilibrium. Okay. So if I have 10 moles of buffer, for simplicity, let's say that I have 5 moles of HA and 5 moles of conjugate base. When our conjugate base and our weak acid exist in equal concentrations, the pKa of the buffer will be equal to the pH. Why is that? Let's take a look at the Henderson-Hasselbalch equation. If I have 5 moles of A minus and I have 5 moles of HA, 5 divided by 5 gives me 1, and the log of 1 is equal to 0. So this component is all 0, thus the pKa will equal the pH. So for this example, when we have equal concentrations of HA and A minus, our pH is equal to our pKa, and the value for both is 5. Now let's say I add in 1 mole of KOH, which is a base. So the KOH, the potassium hydroxide, will break down into K plus, which is potassium ion, and it'll break down into that OH minus. Now this OH minus is our base, and we must neutralize this base. So the buffer is going to neutralize the base. How is it going to do that? Well, our HA, which is in the buffer, is going to combine with our OH minus to produce water and that A minus. So what happened? We utilized one of these HAs and we produced an A minus. So this is going to affect our ratio in the Henderson-Hasselbalch equation. So now we have 4 moles of HA, we started off with 5, and we have 6 moles of A minus, we started off with 5. How does that affect the pH? Now, if we plug in our new values, which is 6 and 4, our new pH is going to be 5.18. So the buffer was able to work to a certain extent. We started off, remember, with a pH of 5, right? So this was a small change in pH. But now let's take a look at another example. Now in this example, we have 100 moles of buffers. So we have significantly increased the amount of buffer that we have. And now let's say that we have 50 moles of HA and 50 moles of A minus, because remember, that's what we're looking at in our equation of our buffer. Now, when we have 50 moles of HA and 50 moles of A minus, once again, 50 divided by 50 is equal to 1, and the log of 1 is 0, so this entire portion is 0. So once again, the pH is equal to pKa, and we are starting off with a pH of 5. Now, once again, I add in 1 mole of KOH. KOH, potassium hydroxide, breaks down into K plus and OH minus. That OH minus, our base, is going to combine with the HA in our buffer to produce water and A minus. Now, once again, we have used an HA, we've produced an A minus, and we have affected this ratio. Now we are going to have 51 moles of A minus and 49 moles of HA. As a result, when we plug in our new values and calculate the new pH, we have a pH of 5.02, which is a very, very, very small change in pH. We started off with 5, now we are at 5.02. What do these two examples tell us? These two examples tell us that when we have more buffer present, the greater the buffering capacity and the smaller the change in pH. So when we had 10 moles of buffer, we had a higher change in pH compared to having 100 moles of buffer, which gave us a very, very small change in pH. Now this correlates to what I said in the beginning. So concentration of buffer, the amount of buffer that we have is directly proportional to the buffering capacity of the buffer. So if we want to minimize the change in pH of a buffer, the more buffer that we have, the lower the change in pH. And that is essentially buffering capacity.